Yeah, hello everyone. My name is Neil Desai, and my project topic is using LLM for enabling offline reinforcement learning. Let me share my screen. S- So, the paper which I'll be summarizing is called Unleashing the Power of Pre-trained Language Model for Offline Reinforcement Learning. The Medium article for which has been already published can be found over here. It is titled Offline Reinforcement Learning Using with LLMs. Now let's start with the summarization presentation. So, offline reinforcement learning with LLMs. Now, what is offline reinforcement learning? Well, in traditional reinforcement learning, an agent learns a task such as playing game by actually playing the game a number of times with different action. And each action has a set of either positive reinforcement or a negative reinforcement. Let's say in snakes and ladder, every time you come across a ladder, you have a positive reinforcement. That means that model wants to, the agent would like to go to the ladder. However, every time it comes to a snake, it will come down. So the agent will learn to avoid the snakes. Well, that is the traditional reinforcement learning. In terms of offline reinforcement learning, the agent doesn't directly play games, but it learns the gameplay looking at previous examples of the gameplay. In essence, this is the offline reinforcement learning where you use old gameplay. Consider it that a footballer is learning to play football by looking at old football videos and not actually playing it. So this is reinforcement learning. Now, what are the offline reinforcement learning? I'm sorry about that. Now, what are the main challenges with offline reinforcement learning? Well, as we mentioned that we use pre-recorded gameplays. Now, with data sets which are sparsely populated or like small data sets, in that case, offline reinforcement learning is difficult. Now, how can we use LLMs to overcome them? Well, as LLMs are trained on extremely large data sets, they possess a sophisticated understanding of sequences and predictions. By fine-tuning these LLMs, we can use their capabilities of understanding sequences and diverse scenarios to provide input to our offline reinforcement learning agents. So what previous work has been done on this topic? Well, firstly, there is using of transformer for decision making. Well, transformer for decision making is basically instead of making a single decision, the transformer makes a decision as a sequence of decisions. So it's like a sequence of predictions. Those are decision transformers. The second type of work which has been going on in this is LLMs for decision making. So LLMs can be used for planning and execution phase for various kind of projects and making the decision based on those plans. Now, the proposed solution in the paper is language model for motion control, or LAMO as the paper calls it. Now, LAMO integrates decision transformer with advanced LM. The fusion of these two brings a great understanding of language model in the realm of motion control. That is how your agent will move in a certain set of situations. Now, Lamo in that the in Lamo the language model you use are well established language models such as GPT-2, or if you look at the latest papers, it could be GPT-3 as well, as they have made it public, which serves as the initial framework. The LLM will serve as the initial framework for decision transformer. Now, this integration is designed to transfer rich linguistic and reasoning capabilities of language models to the domain of decision making in games and simulation. So, LLMs will help provide data and understanding to decision transformers. As you can see, you have the pre-trained language model, the action comes, and then these actions are then passed to the transformers. And then the decision transformer pass it down to the reinforcement learning agent. Now, what is unique about LaMO? So first is the fine tuning. So when we fine tune the large language model for our offline reinforcement learning, we do not fine tune the entire model. We find not all parameters. That is what you would be doing in traditional uh, transfer learning or such other cases with CNN or RNN or so on. In this case, you would be only fine tuning a small number of parameters in the language model. This is also called as low rank adaptation. So as only small portion of the LLM are fine-tuned for as per our requirements, the model will understand our business requirement or the problem which we are trying to solve. At the same time, it will also be able to maintain its decision-making task and its ability to understand sequences. The other uniqueness about Lamo is it doesn't use a simple embeddings. Instead, it uses more complex, multi-layered perceptron embedding. This allowed for processing of different kind of input data. The third is auxiliary language prediction loss. So since here you are using LLMs in conjunctions with decision tree. So there are two different things which first is your language understanding and second is the action cause of the decision tree. So there are two things which are being predicted. So they have come across a loss function which combines both this together. So as you can say, to maintain the language model's proficiency in language understanding and generation, Lamo incorporates an auxiliary language prediction task during training. This additional objective ensures that while the model learns the decision-making strategies, it doesn't lose its inherent language capabilities. Now that is how Lamo works. Now coming to performance. Well, Lamo was tested in various scenarios, such as the Muju simulation, the Atari game, virtual kitchen setup, and the result shows that it performed well in this task when the reward and the data was limited. It performed better than the existing traditional model and even the standard decision transformer. In dense reward tasks where data is abundant, Lamo's performance is competitive, though it's not always dominant. This illustrates that the still present strength of traditional value-based methods in offline reinforcement learning scenarios. Limitation. Now, its performance in dense reward tasks. What is the limitations of Lamo model? Well, its performance in dense reward tasks where data is abundant. Sometimes this comparable to traditional models, but it doesn't always outperform them. In a lot of cases, it performs worse than the traditional model. And the second limitation is the auxiliary language prediction loss function. The auxiliary loss function, which was one of its uniqueness, which allows it to train the model at the same time, making sure that the language model, the LM doesn't lose its language capabilities, doesn't universally boost performance across all tasks. Conclusion. Lamo stands out as a pioneering framework that effectively marries the advanced language understanding abilities of language models with the strategic decision making required in offline reinforcement learning. Its prowess in sparse reward tasks and exceptional performance in low data scenario underscores the potential of language models in enhancing the offline reinforcement learning methodologies. Thank you.